Hi everyone. So I see people are starting to trickle in, which is good. Today we don't have any visual support to go with the presentation, so it's mostly going to be a discussion here with Avihu, Shahar, and Shahar about recursion. A specific speaker, a conference speaker.
We have a clear one speaker, so I'm probably doing some advertisement, but it should be a good one.
Perfect. All right. So you have one Shahar with you, right?
I have two Shahars now. Before I had one, now I have two.
Yes.
Wonderful.
We just wanted to make it easy for everyone, so we took the two engineers with the same name. No, I'm joking, but this is how we split the effort here.
I'm actually you know what? Let's start the community call. So welcome everyone to our community call. Sorry, you'll have a way to catch it up later on. Actually, I'm not sure it's going to be recorded. So if one of you, I know some of you sometimes record it. If you can record it and then share it in the channel, that would be very valuable, please. So welcome to our community call. Today's topic is going to be a recursion. So to give a short intro about recursion. Recursion is something we've been talking about for a while. We released a blog post called Fractal Scaling about it a while ago. But I think your talk in Prague was really a aha moment for a lot of people. It made things a lot clearer. I think a lot of people thought, oh wow, I didn't think about that application or that one. And some community members were curious to hear more about it. So, which is why we're talking about it today. So thank you. First of all, thanks for coming. And today we're 4 people on the call. So there's me, Henry. We have Avihu on the call, and we have Shahar and Shahar. Can you guys say a few words about what you do at Starknet, please?
I'm an engineer, Starknet. I worked on Recursion in Starknet and Cairo.
This is Shahar Papini. This is
Shahar Papini. Okay.
Yes.
And I'm Shahar Samocha. I'm working as a software engineer on the shell prover system for almost 2 years.
Super cool.
Yeah.
And Avihu, you're head of product.
Yeah, hi. I'm here as well.
Very cool. So I'll start with the first question. Is it random or is it something that was consciously chosen that both people working on the two ends of recursion are both called Shahar, so it's kind of a recursive naming system, or it's random?
Yeah, I think it's random.
Okay, cool. So maybe we can start the call with a small introduction. Like, Avihu, if you can introduce in like 5 minutes, if you can give us a very summarized version of what recursion is and how we started working on it, that would be great, please.
Yeah, I think I will only speak 5 minutes because you have the creators here, so it's better to give them the stage. I will do to my presentation basically what Recursion is doing, which is I already processed it once or twice, so now instead of taking an hour and then 20 minutes, we'll just take 5 minutes, which is also the basic concept, so it's nice analogy. So what we want, maybe I will start slightly differently than what I did in the presentation. What we want, I will start with the goals and not with what recursion is, and then I will explain it on a very high level and we can go and deep dive into it. So what we wanted to achieve with recursion are basically 2 main things, and we achieved a few more things with it, but the 2 main things we wanted to achieve is we wanted to increase the capacity of what we can prove. You can think about in a given time frame or using a given gas cost, and reduce the latency of how much time it takes us to prove those things. And this is basically the main goal that we are trying to achieve here. But there are many other nice benefits that we can touch during the call of recursion. So what is recursion in the context of proofs? It basically means that so far you are all used to the following concept. You have a program, you write it in Cairo, you prove it, and then you verify the proof. And that's how you know things are working normally. Running the prover takes some time, which is somewhat related to the original computation time. So let's say 100x or 1000x over the computation. And verifying is very, very short. You can think of it as if it's not too complex, then you can think of it as a log t of a computation of length t. And if not, it's practically close to a constant time. And what you do with recursion is you take the verifier, which is by itself a program, and you're not using it as the last step, but instead you prove the running of this verifier program as another step. So instead of like verifying a proof, you can verify the verifier verifying a proof. And you can continue this on and on. And because we said that the verifier runs in time much shorter than the original computation, then also proving the verifier typically takes much less time than proving the program that was originally targeted. And this beautiful advantage is something that we can use to now increase our capacity and decrease latency. Increase capacity because if before we were limited by t steps, so now we can take those t steps, generate one proof, and now we can prove those t steps by proving the verification of this. So it's only log t step, which is much, much smaller. So to the same imaginary box of t steps, we can push many, many smaller boxes of log t steps, and we can basically prove many programs where previously we could prove only a single program. And latency is reduced by the fact that you can prove many of such programs in parallel and then take any two proofs that are the outputs of the first proving step and proving the verification together, which cause everything to be run much nicer in parallel. And that's it. I think those are like my 5 minutes. I don't know if it was crystal clear, but let's dig into it with the experts we have here.
No, that's great. It is very clear. So if I can ask, so you mentioned Shahar Papini and Shahar Shamaha are both working on the two ends of recursion. Could you guys give us a rundown of what these two ends are?
Yeah, I mean, the first end I'm working on, I'm Shahar Papini. It's actually writing Cairo code that verifies a Stark proof. It's basically it's Cairo code. It verifies some mathematical things like evaluating the polynomials and doing these miracle proofs, all the Stark things. So this is one side, writing the Cairo code that verifies it stuff.
So this is equivalent, so this end, sorry for cutting you off, so this end is equivalent to what the verifier is doing currently on Solidity, right? So it's basically writing a smart contract that does the same thing on Starknet that is done on Ethereum, actually, currently.
Wait, it's not a smart contract. Yes, today we have a verifier written in Solidity, we have a verifier written in C++, and now we have a verifier written in Cairo. Now it's written not as
interesting.
Starknet contract, it's just written as Cairo code, which can be used in Starknet contracts, but also in a lot of other places, like in Sharp.
Yeah, so I'm Shahar Samocha. I worked on adapting Sharp to use this Stark verifier that is written in Cairo, such that if Sharp until now could take some Cairo logics, pack them into a single proof and send them directly to the blockchain for verification. So now instead of sending this proof to the blockchain, it can create a verifier program written in Cairo, feed it with the input with the proof as an input, and send it back to itself with a program that wants the verification of the original proof. So now Sharp has the recursive feature of sending a verifier job to itself.
I also want to make some small distinction here. Note that even today, Sharp without recursion, it can still prove a few programs together. It does so, but just because Sharp has a Cairo logic called the bootloader, which can just call different Cairo programs from one big Cairo program, which is the bootloader. So it was able, and the Shachar Samocha added a feature that it can also not just run Cairo programs, but verify, call this Cairo verifier and verify a lot of programs and treat them as if they were just programs running on Sharp.
Okay, so I think I understand. So correct me if I'm wrong. Basically, Sharp up until today was a Cairo program that had a bootloader that was able to load other Cairo programs and then aggregate these into one bigger program that gets proven and sent, and the proof gets sent to Ethereum. And what you're doing now is, instead of loading these programs directly, you're loading a new program, which is a Cairo verifier, and you're feeding the programs directly to this verifier.
Not exactly. I think that in the old setup, like you could take multiple Cairo logics, no matter if the same or no, wrap them into a single proof and send it to the blockchain, to Ethereum. But now, instead of send this proof to the blockchain, we can create a new verification program that is written in Cairo and send it back to Sharp to be later merged with another.
Bootloader in a lot of places right now. It's also verifying proofs of other bootloaders, but it's also still on the leaf of this big recursion tree. It's in every node in the recursion tree. This bootloader appears, basically.
Wow, that's really interesting. And so, okay, so you can basically send a program, generate a proof for it, and then send that proof to another Cairo program that generates a proof that you verify that proof, right? And you can do this various times, and it shrinks the proof size every time, and so it saves verifying time and resources on the other end, on Ethereum.
Yes.
Right? Where do we stop? What is the criteria you guys have in mind when, you sent it once, you generated a proof, and then you send it a second time? Why does it make sense to make it, I don't know, I'm just giving a random number. Why does it make sense to do this 2 or 3 times and not 3,000 times?
Generating proofs is take time, so you pay for that with latency. If you don't want the jobs to have too much latency, you have to at some point send it to the block.
Yeah, I think it's worth explaining a little bit more on this step.
I think I want to say that, like Aviv mentioned, there are 2 reasons why we want recursion. One is, yes, making small proofs, but the other is also for making them in parallel. If you think about the goal of making them in parallel, it makes, like, you get straight away what kind of recursion you want, pretty much. You want to take the smallest parts you have and proving these small batches and then aggregating them together. So that is from the parallelization side. Now, I think that today we with regards to the proof size, we treat it as more or less as a constant because they don't change all that much. Log squared on these kind of ranges is pretty much the same. So it doesn't really pay off, I think, to just prove a verification of one program. But we don't really do that. Do you want to add something?
So it's more for parallelization. Understood. And so parallelization can be used, Aviv, in your talk, you gave the example of having different jobs coming from different apps, or if tomorrow there are various Starknet chains. You can imagine having various app chains sending their job. Can you use parallelization when processing a single chain also?
Yes, definitely. So did you guys speak a little bit about Sharp?
People are familiar, but a refresher would be useful for sure.
Yeah, I think it's worth mentioning. So Sharp stands for shared prover, and the basic idea is that it can take different jobs where every job stands for a Cairo program and some input. And typically this input is just a list of transactions. So you can think of Sharp as a machine that can take a logical machine that can take many different jobs. They can be different in the input to the same program, but they can also be different in the program itself. And it creates a single proof for many, many different jobs. And so Sharp doesn't really care if you feed it with one batch of Starknet transaction and another batch of Stark X version 3 transaction, or if you feed it with 5 blocks of 5 different batches of Starknet. From the Sharp perspective, he will take any list of jobs up to some limit and will unite them to a single proof, and that's what it does. So to answer your question, even if it's just Starknet running on top of Sharp, and let's say every block is a separate job for Sharp because it has different inputs of like a set of transactions. From Sharp perspective, it will take every block, prove it separately, can be done in parallel if there are many blocks waiting, and then unite those proofs in a recursive way until it will reach a single proof, and then we'll submit it to chain. So you will enjoy parallelization and increase in speed, like reduced latency, even if it's a single app. It doesn't prevent it from being used.
So it's a single app, but with a lot of transactions
Right.
on it. And even if they are dependent, it doesn't matter because they can prove it independently.
Yeah, that's an important point. I wanted to make one more comment, Henry, if I may. Maybe it's not clear, but the verifier program that Shachar wrote has some basic size in Cairo, and then also, correct me if I'm wrong, Shachar, but it also has a cost that varies with the size of the proof. So this cost will get lower by the level of recursion, but there is still a fixed cost of some Cairo program that represents this verifier. So it won't get infinitely small.
It doesn't really shrink. More like it converges to this constant.
Yeah. That's one extra comment I wanted to say about the previous discussion.
Yes.
Okay, very cool. Makes sense. Thank you. I'm curious about how did we get started working on recursion? Because like from an engineering standpoint and from a mathematical standpoint, it's a fascinating topic. I mean, validity proofs in and of themselves are fascinating, and recursive validity proofs are fascinating. But I find it really interesting that we're really talking about concrete stuff, right? Reducing costs, reducing latency. When did you guys start working on recursion? When did it first come to your mind that, oh, we could have recursive proof? And when did it jump to your head that, yes, we need recursion for that? Is it something that was in the air for a while? Did you start working on it straight at the beginning? How did you guys actually implement this thing?
Well, first of all, I think that the idea of recursion was known to us from the very beginning. It's like a theoretical result, and that was known, and other people were doing recursion for other systems.
Right.
Yeah, so it's not something that we invented in a way. So it was in our minds all the time, and I think when we first thought about the CPU or Cairo, we said, it's zero computation. It will be great for recursion. It will allow us to do recursion. So this was also in the back of our minds. Though I think it stayed there for a lot of time without actually starting the work on recursion. Why did the work on recursion start? Because, I don't know, we had time.
Yeah, I was also curious. I think it's a very good question, and I would also be very curious. When did we start working on it? I think it was more, I don't know, maybe it was Shachar initiative.
Yeah, it's more like I wanted to work on Crust, and people didn't want me to work on Crust, so they gave me other things to work on.
But I want to explain a little bit more on the context. It's important to understand. So I heard people talking about recursion as early as, I think, over 4 years ago. I remember one talk from one of the Solidity creators, Christian Reich or something, some long German name. Apologize, I cannot pronounce. And he was mentioning recursion even back then, but it was a theoretical concept. Over the years, other systems implemented recursion, but we haven't. And one of the reasons that now it's much easier is because of Cairo. This is what Shachar was mentioning. The fact that we have Cairo makes our ability to implement recursion and even more be flexible with recursion, like much greater ability than what we had before. We don't have to deal with all of kind of nasty stuff or with less nasty stuff.
Yes, so we can do also a lot of optimizations that aren't really very hard to do without this general computation, which is Cairo.
Okay, understood. So what you mean is that in the beginning, it was theoretically possible with proof, but writing proofs was difficult in and of itself. So thinking about recursive proof was a very high level of difficulty. But now, like once we got Cairo and we got the ability to write general purpose programs that are provable, it draw the line together much closer. And so, Shahar, as you mentioned, you wanted to work on Crust, which is Cairo over Rust, right?
It's out of scope. How much time do you have?
Okay, so you'll have to come back, sorry. But okay, let's not talk about Crust for now. And so you focused on recursion. When you started focusing on recursion, because I think there's we're talking about performances, but obviously recursion is also, I mean, what I found fascinating with proofs is that it's the first paradigm where I see two chains talking with each other. When Ethereum validates a proof of Starknet, it understands to a certain extent what happened on Starknet, right? It's able to verify it without talking to a human. Having recursion really opens up the door to having a multi-layer cross-chain communication system. So there's the engineering side of having lower latency, lower cost. There's also the product side of it, of having various chains interacting with each other. When you started working on it, it seems like obviously you took it from the engineering side more than the product side, but can you talk a bit about this difference? Like once we have something that allows to have a more efficient sharp prover, how far are we to having chains like Starknet chains that settle on Starknet?
Yeah, talking about the concept that we sometimes call layer 3. I think it will be an outcome of this recursion in the following sense. Right now, we have a Cairo program that represents a verifier. We probably need to do some changes for it to be deployed on Starknet. But once we do those changes and you have a Cairo verifier on Starknet, you can now run sharp proofs against this verifier. And what that means is that you can take Starknet or StarkX or practically any other Cairo program and verify it not on Ethereum, but on Starknet directly. And what do you gain by it? So, first of all, verification will become much cheaper than on Ethereum because it's Starknet. So data is cheaper, computation is cheaper there. Those are great benefits to verified proofs. Except that if you have two systems that communicate over Starknet, then the communication cost itself is cheaper. But I want to dive a little bit deeper. It's actually an idea that I first heard last year on ECC from Shachar here. It was about different VMs. So one interesting concept is that I'm diving here like very deep. So if it's over the head, tell me, and we
No,
can
please,
discuss.
that's perfect. Let's
Okay,
dive.
so here is a question we got a lot a year ago. Why don't you want to support? Why don't you run native EVM and instead you go with Cairo? And I think that by now this question is more or less settled. But let's say that tomorrow morning someone comes and he say, I understand StarkX, I understand Starknet, but I want my own VM. Why? I don't know. Maybe because you want to prove EVM steps, or maybe because they want to prove some whatever Orbit VM, or I have no idea, MIPS, or whatever VM they have in mind. So what I can do, I don't promise it will be efficient, but it will be more feasible, is that they can implement their VM in Cairo, like every state transition of their VM in Cairo, and then they can use the verifier that we wrote in Cairo to verify those proofs. And the reason I find it interesting is because now you can have different environments on Starknet. The basic environment still operates on Cairo, but maybe you have a different environment that is, for example, EVM compatible, and people deploy their smart contracts that speaks EVM, and whenever they want, they go out of this ecosystem and they speak to the other ecosystem with some messaging system. So kind of an environment where you separate different execution layers, but at the end of the day, they can all communicate with each other. So I think it can be an interesting concept.
I just want to mention that another way to use it is maybe zero knowledge. You can't really use token to zero knowledge because the prover is someone else and you can't give him your personal information, but you could do it yourself. If you have this program that needs to have zero knowledge inputs, you can prove it yourself, and on Starknet just have the verification of this program, and just you keep your zero knowledge.
I mean, you're assuming that people can prove things themselves, so that there's a prover that they can use. So if they can use it, then probably there are also various sharp providers also. But yeah, I also think that this is also another question I wanted to ask you guys. So because we can go into the performance side, we can go into the multi-chain side. This also opens up the door to having client-side proofs, right? So you could use this for privacy reasons, for a bunch of stuff, right? I could generate a proof on my phone and have Starknet A# process verified on Starknet, right?
Right, as long as you have a proof system that matches this verifier, you can use it to prove your own stuff on Starknet.
This is really interesting. What I find fascinating with these systems is that it seems like in some way it mimics the architecture of the web today, in the sense that it allows systems to specialize and separate. You can silo them, but you also have a unified layer at the bottom for them to communicate and exchange. Anyway, thanks. That's a great insight, guys. So can I ask, in concrete terms, where are we standing now? How far along are we with the development of Recursion? And we're not asking for commitments here. We're just curious where you guys are and what are the next steps you guys are looking for in the development of Recursion.
So we already have a working POC version of the recursive sharp that actually absorb every data that's sent to sharp on mainnet and prove it by itself and settle it on Gerli. It's really in early stages, so we don't have the numbers yet of the improvements, but we have a working version of this.
So wait, we already have a recursive proof that's settled on Gerli?
Yes.
Yeah,
I'm going to quote Louis here. Did you tweet?
Yeah, normally on the engineering side, we wait a little bit longer before we tweet, but I do want to stress it a little bit more. It's not just an environment on testnet, it's an environment on testnet that basically execute whatever production sees, right?
Mimics it.
Yes. So it's a mirror environment, basically.
Yeah.
Oh, okay, so you mean so it could take what is today managed by Sharp and execute it, like in this POC, you could execute it, right?
Right. We are executing it.
Now executing it.
Yeah.
We have another prime system, like a system that mirrors all the inputs from the build system and just uses Recursion, and it's running right now.
Okay, so it's basically like, it sounds like it's right around the corner.
It's not very far. That most of the questions that are delaying it are us being more cautious. So, Shachar, maybe you want to talk a little bit about the audits and so on.
Yeah, we did like an internal audit of this. I mean, this is the first step, just to make sure that everything looks sound and okay. And there are a bit of mostly documentation changes that need to be added. But after this, I think we are considering making an external audit.
Correct.
Right?
Yeah, I'm not sure. I think the few things that are getting there is some technical issue in adding another built-in, which is that is not related to Recursion. And then there is a 28 days delay on upgrading everything on mainnet. And there is an external audit that maybe will happen in parallel. So I think practically we are looking at between a month and 2 months before it's running on mainnet. That's the not committing on exact timelines, but ballpark. That's what we are looking.
Yeah. Also, I think that Kinetic is working on another improvement.
Right. Worth mentioning.
It's very like will make it a lot more efficient. And I think it's also around the corner, so maybe we would wait for it as well.
Yeah. So I think you can, like, not officially timeline is a month or two before it's running in production, and I think it's also worth talking about the roadmap for the.
Definitely. Yeah, so what's next? So in the next 2 to 3 months, we'll probably have it on mainnet for Sharp. What's next?
A lot of things. You want to talk about Kinetic improvements and the scheduler and the plans?
I know the schedule. Schedule is something interesting.
Okay. So basically, Sharp faces the problem of online scheduling. Like, it gets Cairo jobs to prove, but it doesn't know how many jobs it will get, and it wants to make as large as proof as it can to be settled on chain, because that results in a lower cost per transaction.
Yeah, I mean, it has the freedom to choose which jobs to prove together in recursive jobs. And this freedom, if you knew all the things we'll get in the future, it will maybe easier, but it doesn't. So we need to make some assumptions.
Yeah, so in the old version, Sharp had to choose which job to pack with another to a single proof. But now it has another decision to make. You need to choose which jobs to take into a proof, and whether to send this proof to the blockchain or send it to Recursion back to itself. So the online scheduler become a way more complicated than it was before.
Yeah.
I mean, it sounds like it's more complicated, but it's also easier because in one case, you have to choose which job you pick before proving. And in the other case, even if you take too big of a job, you can always reduce it down the line to fit the actual proof, right?
There are also deadlines for jobs, so you need to be careful when you match them. I mean, you don't want to. Maybe you only have 2 jobs right now, but one has a big deadline, the other has small deadline. So do you match them together or not?
Makes sense.
Yeah. Okay, and I wanted to talk about the improvement that Kinetic is working on. I just mentioned. Basically, it relates to the hash function. A big part of the Star protocol is Merkle proofs. Now, the Merkle proofs are using hash. That on one side we want to be efficient in modern architecture, in x86, in our computers, because eventually there will be a prover that computes tons of hashes on things. You want it to be fast. But on the other hand, this hash function will also be run in the Cairo verifier, which is written in Cairo, and So we wanted to be efficient in Cairo as well. So the verification in Cairo wouldn't be very expensive. So, okay, we don't really have a hash function that is good for both, but we noticed that not we can combine hash functions, because if you look at the Merkle tree, for top layers, the prover needs to do less of these hashes, and in the bottom layer, it needs to do a lot more. But the verifier only checks a single path, so they're equal to him. So if we mix this, if we say the lower layers are friendly to x86, to the CPU, and the upper layers are friendly to Cairo, then we get a good something in between, which this would make the prover not a lot more expensive, like in the same order of magnitude, and the verifier would be a lot more cheaper, like maybe 10 times, something like
That's
that.
the estimation.
Yes, the estimation is 10 times.
Wouldn't this mean that you need to change your prover also?
Yeah, our prover is modified, yes.
Okay, so you need a prover for higher layers and a prover for the ones that get
No,
settled elsewhere, no?
Prover, it's a configuration, you can call it.
I think that's part of the power of Cairo, right? So you change the program, but from the prover perspective, it just knows that this hash function is implemented in Cairo or built-in, and this hash function is also implemented in Cairo or built-in. It's basically you change the program, and now the prover has some configuration on what is the amount of hash function from type A. Let's say type A is fast to compute, slow to prove, and type B is slow to compute, fast to prove, and it just makes the two in a way that is optimized.
I mean, you are talking about proving the verification.
Right.
Yeah, but they're also proving the initial program. It now needs to use the other.
Right.
That as well. So
right.
C++ prover needs to change as well.
Okay.
Yes.
And I think over time, by the way, I think that over time we will continue to touch this place, in a sense that for now we know to optimize some specific hash functions, and we have a built-in for Pedersen in particular. But in the future, we might add more built-ins for hash functions that enjoy from both like faster computation and shorter time to prove. So it might be the case that we will even further optimize there.
While you mentioned built-ins, can you talk a bit about that? A few months ago, I asked you how many built-ins will we get? Will we get thousands of built-ins? Like putting aside the fact that they're really specific and hard to produce, would we get in Starknet like thousands of built-ins? And you mentioned no, there's a cost to them, so we won't have a lot of them. But from what I understand, now it changes a bit with Recursion, right?
Yeah, it's a very good.
I mean, there's also the adaptive layout.
Let's maybe start by you explaining what a built-in is and why is it important.
A built-in. Error is like a bunch of polynomial equations that verify something. We have an error for Cairo that verifies Cairo instructions that their execution is valid. We have an error, again, a bunch of polynomials for Pedersen. We have an error for Ketchak and for range checks, etc. And we can take all these bunch of equations and throw them into one big system, one big error that verifies both this. So we can imagine that we have a CPU component that has Cairo instructions, and it's alongside another error that has Pedersen instances, and alongside another Ketchak instances maybe. So we have a lot of things living in the same error, so we can verify 16 Pedersens and 32 Cairo instructions and 4 Ketchaks in the same error.
So that's an honorable comparison, right? But you're talking CPU, so it's kind of like if Cairo was a specific chip, and for specific operations, it would send instructions to another component, which would be, for example, a graphical card, right?
Yeah,
and these would be the built-ins.
That is true. It's like hardware, you can say. Everything is in our computer. Everything is an integrated circuit, and in the air world, it's a bunch of equations, but they're all living together in the same box.
So when you're doing a Pedersen or a Ketchak, you're basically it's like if you were calling a graphical card on your computer, it's sending to another chip, basically, in your computer.
In a way, yes.
Okay.
I mean, it's worth mentioning the way that these parts communicate, and they are communicated through memory, through the Cairo memory. So yeah, basically it's like if you had in the real world components that talk through memory, then it would be very similar. Yes.
So that was about built-in.
Yeah, that's all about built-in.
Cool.
What is it? Yeah.
And actually the Cairo verify, the recursion feature also gives us an improvement that is specific to built-ins. As if until now each built-in that we wanted to add induced a lot of constraint on the solidity verifier, which make it more complex. Now, no matter how many built-ins we have in our original logic, if we only prove a Cairo verifier program on Ethereum, we only need the built-ins that we need for the Cairo verifier program. We don't need all the original built-ins that we used for the original logic.
Yes, if we think about the recursion tree of programs that prove verification of other programs, then the solidity verifier only needs to verify the top, the root of this tree, which is its layout is a lot more maybe thinner, consistent. We know it looks like it's basically verifying some program, and not maybe all the diversified programs you have on the leaves.
Yeah, the point is that today adding a verifier, adding a built-in to the verifier can be very ugly, meaning complex the verifier and increase the gas cost by a lot. And we don't want that. And with recursion, we can stop doing it for every built-in that is not used by the recursion step, which is amazing.
It basically allows solidifying the lower part of the stack, so the solidity verifier, and not touch them anymore and push built-ins development some layer above, right?
Yeah, almost not touching them. Yes.
Oh, that's really interesting. Okay, that was my question about built-ins. I'm looking at the.
I want to mention maybe plans we have on the works for the adaptive layout. Like, for right now we have like a specific set of layouts which says, and that basically says which built-ins are in this proof and what is their ratios. I mean, for every Cairo instruction we have 4 Pedersens or something like that. And we have like a specific set, and the scheduler needs to choose the best one. And a lot of the time it makes a lot of unused things, a lot of waste. Because if the best layout we have doesn't use like half of the Pedersens in this layout, then they're going to waste. We are still paying for proving them, but we're not actually using them. So we have this concept of an adaptive layout that we can choose any combination we want, like on runtime for our layout. We can say, these programs only use this much percent and this much instruction. So we'll like play with the error on the fly and decide where all the columns and polynomials go. And then we have this layout, and the verifier will also be dynamic and know, okay, I can move these columns, and I dynamically know this error, and I can verify it. And this leads to a lot of cost savings in the usage of built-ins, mostly.
This is really interesting. Thank you. I just want to mention that we have about 180 people listening to us. I see no questions in the community calls channel, so I'm pretty sure everyone is a specialist in recursion and understand everything. In case some of you have questions or have things that they don't understand, please ask questions. It's important. We're here for that. So you can ask them in the community calls channel, and we'll be happy to answer. Okay, so thank you for this technical deep dive. It's really, really interesting. Wanted to ask something more like, okay, so now taking a step back, where do we go from that to um, being able to use recursion and recursive functions easily in Starknet? When will it be as easy to deploy your own Starknet and have it settled and verified by a public Starknet as it is to do it with, I don't know, Geth or Cosmos?
A good question. I think the first, there are a few steps here. I don't think any of them will take too long. But the first thing to do is first take out Recursion to be live. Then probably we need to adapt both the verifier in Cairo and Sharp to work with Starknet. So that will be the next step. And once this is done, we will follow by adding both StarkX and Starknet to be able to run on top of Starknet as a layer 3. So this is on the technical roadmap for, I don't know what, the next 6 to 9 months. And then the only thing that you would need, obviously people could write their own whatever SDK to deploy Starknet, but the only thing that you would need, if you really want to deploy everything and run everything by yourself, then you would also need a prover that you could run against it, right? So that's something that I don't know what's the timeline to release, but I'm pretty sure it will also be available at some point.
Yeah, for sure. I mean, we talk about the decentralization of Starknet, having an open source prover. I mean, having a prover that anyone can use is a prerequisite for Starknet to be decentralized, so it will probably come along with that, right?
Yes.
Okay, cool. So it's not too far in the future. So within the next few months, we're going to see the first recursive proof to have efficiency gains. Then within the next year, hopefully we'll see the first L3 emerge. Where do you see this going, like 5 years down the line? What do you think the landscape around Starknet and validity rollups look like once we have usable recursion?
5 years ago, there was no Starkware, so.
I know.
I don't know
5 years. 5 years is a long time, but that's what makes it interesting. And
It's
it's
for
just
a year and a half, then it's
Yeah. I mean, I hope Starknet will be decentralized by then, and you will have your prover, and it will be on track. It will be used, and the major changes will be, I don't know, some protocol changes, any built-ins, DAO decisions. I think that this year and a half is mostly about decentralizing, making everything easy for developers, for users, making it comfortable. It's hard to see past that.
Yeah, I also think that one interesting, if you want more further prediction, right? So let's say in the next year or so, we are working very hard towards decentralization, which means it's not just opening the prover, it's also creating some leader election or consensus mechanism on top of Starknet, releasing a sequencer, working on peer-to-peer for full nodes. It's also for this is not just open sourcing some code. I think once this is done and out there, it will be interesting to see what path people are taking. Is it running layer 3s that are forks or replications of Starknet or StarkX, or will people actually take the path of writing their own Cairo programs for different operation systems? This is more far to the future, and I think Cairo can be used in many ways, and Starknet is a layer that we try to make both decentralized and very flexible. So yeah, who knows? But that will be interesting to watch.
Yeah, for sure. I'm looking forward to I hope one day Starknet or validity proofs can be used to enable easier cross-chain communication. Like if Starknet is able to understand, like to have a storage proof of what happened on a chain and then on another chain and serve as a kind of, I'm not sure if it's a hub in the middle or what it is, and I know there are way more complex things around that than just recursion and storage proof. But I'm really curious to see what could happen with that.
I can mention that there are a few projects that are working on all kind of implementations of light client of other chains. So in Cairo, so once you have that, let's say you have a light client implementation of Bitcoin or something that knows to verify Solana consensus and state to some extent. Then when you deploy it on Starknet, if it gets information from the external world, it can verify it the same way that light clients do. And on Starknet, those kind of things may be feasible. And then you can get what you mentioned.
That's really cool. So atomic swaps, cross-chain, settled trustlessly, for example. Okay.
Yeah.
Look, we're about to reach the hour, and I've asked most of the questions I had. I propose we wrap it up. Do you guys have something else you wanted to mention or to discuss?
Yes, but it's a lot of fun to speak with so many people about these topics, which I considered exotic, maybe not rightfully so.
I think
Yeah.
the community is really interested in engineering, like engineering in general and engineering at Starkware in particular. So like it was a pleasure to have you. Thanks a lot, Avihu, Shahar and Shaha. It was really enlightening, and it's super interesting to see how these things we use every day get developed. So thanks again.
Yeah, thank you very much.
So to all of you listening, thank you for your time. See you in 2 weeks. I'll try to make a fixed time next time and to commit better to it and to find a way to be both on YouTube and on Discord. In the meanwhile, I hope you enjoyed the call, and don't hesitate to ask follow-up questions. Sometimes these things take time to percolate, and we'll try to answer them once you guys answer these things. So thank you again for your time, and until next time.
Thank you. Bye.